Hi, my name is Ruslan, and I would like to present our work titled The MonoForce Learnable Image Conditioned Physics Engine. Reliable navigation in wild unstructured environments requires an accurate model that predicts the robot's behavior on complex terrains from onboard sensors such as cameras and LiDAR scans. Given an RGB image on the left side and control commands, the robot's terrain interaction model predicts terrain properties and possible robot trajectories. We propose a data-driven and physics-based architecture. Thanks to the differentiability of all its components, our model is trained end-to-end. The first part of the model lifts the calibrated camera features to 3D. The next convolutional part predicts terrain properties like geometrical shape, vegetation suppression, and friction. They help to estimate robot terrain interaction forces. Finally, our physics engine delivers the robot's trajectory. Since the model is end-to-end differentiable, the trajectory loss gradient is backpropagated to update the model weights. To improve the learning, we introduced auxiliary losses. Firstly, a geometrical consistency loss matches the predicted height map with the corresponding LiDAR scan. Additionally, we use the semantic pseudo-labels provided by the foundation model segment anything. In this way, we refine the terrain height map, ensuring that only rigid objects like stones, walls, and tree trunks represent obstacles. Given a single calibrated camera image, the model provides height map shape, friction values, described by the height map color, the robot's trajectory, and interaction forces at contact points for a specified time horizon into the future. In this case, the model successfully suppresses small vegetation in front of the robot. We also demonstrate that the released physics engine outperforms its data-driven LSTM baseline in terms of trajectory prediction accuracy. It is also capable of generalizing to out-of-distribution cases, such as falling from a cliff that is not present in the dataset. We perform autonomous navigation runs with the MonoForce model. For each input camera image, we predict a bunch of trajectories for different control commands and select the one with the smallest robot-terrain interaction cost and waypoint distance for navigation. It is demonstrated that the robot is capable of going through hanging tree branches, traversing high grass, and at the same time avoiding tree trunks and other obstacles. Let's have a look at the prediction examples. In the first row, we can see input onboard camera images. The second row demonstrates the predicted height map around the robot in top-down view. Lastly, we visualize in 3D the terrain shape and predicted and ground truth robot's trajectories. The color of the height map denotes friction values. For example, the model predicts the highest friction value for the paved road. We also demonstrate that the MonoForce model is capable of accurately estimating terrain shape and possible robot trajectories in a diverse set of scenarios and environments. The green color of the trajectories represents lower cost, while the red one marks potentially dangerous robot-terrain interaction behavior. Thank you for your attention, and feel free to check out the code and data sequences in the project page.